Hey guys, so in this lesson we are going to recap the equations we came up with last time. The three equations known as your kinematics equations. We have that final velocity, initial velocity plus acceleration times time. That was from the slope of the graph. We have the displacement there equals VOT plus 1/2 AT squared. Remember that was from the area under the curve. And then we combined some equations to get rid of that time factor to give us that third equation there, VF squared, VO squared, plus 2A delta X. These are the three kinematics equations. We said these are good only if your acceleration is constant. We're going to talk about a couple examples where accelerations may not be constant, or show you how calculus can help give you the same equations that we have here. Looking at this graph here, we can see the velocity is changing as time goes on. I can tell the velocity is very low in the beginning. It's increasing on a curve, and then it's kind of leveling off at the top there. And looking at this graph, this is not a nice constant increase in velocity, which means we don't have a nice constant acceleration. Two things they're showing you here is that if we look at those areas up and down, each of those areas would add up to our displacement, because the area under a velocity graph tells us how far something's traveled, and the slope at any point would actually give us the acceleration of the object. In this case, the acceleration is not going to be constant. The acceleration will be slow in the beginning, it'll be higher in the middle, and back to almost zero at the end. When we look at examples of using calculus to solve problems, if we're taking slopes of lines, we're taking derivatives of a certain equation, and if we're trying to find the area under the curve, we're taking the integral of that equation. Or like we've done in our calculus practice from the summer, we're doing the reverse of what we did. Instead of taking slopes, we'll do the unslope, or the reverse of taking a derivative. So we've seen several times here that if I've got a position time graph, let's just say the position time graph looks like that. What that's going to do for me is I'm going to be able to identify the velocities as a function of time, and also the accelerations as a function of time. Taking slope, I have that red line there, I could have a red line there, or a red line there. All three of those give me three different slopes of the position graph. So if I take the change in position over a change in time, we know that gives you the instantaneous velocity of an object at any moment. The velocity time graph would be extremely negative, not so negative, and then zero. We see a decrease in velocity from a very high negative value, which just means going to the left, to zero. And if we take slopes of this, the change of velocity with respect to time, we now know is the acceleration. So the acceleration value is the slope of velocity. Or another way of writing acceleration is the second derivative of position. So if I give you a position equation and you take the derivative twice, you'll get the acceleration. What this will show me is that my acceleration graph, if I get the slopes all across there, is a nice, steady, positive value. And that's for a scenario where acceleration is constant. Now in some of the examples here, you may come across a scenario where accelerations are not constant. And what that would look like would be if you had, say, my position follows a t cubed route, just to do a simple example here. Knowing the derivative of x with respect to time, so my velocity would be 3t squared, the acceleration would end up giving me 6t. So that is not a steady acceleration. That is an acceleration that is increasing as time goes on. So an example could be if you were pushing down on a gas pedal and your pressure on the pedal got higher by 6 every single second that you're pushing your pedal down to the floor. That would be an example of a non-constant acceleration. Your position graph would be a cubed function, so very steep like that. Your velocity graph, a parabola, which means your acceleration graph would end up being a straight line. So you could take the derivative again if you'd like, because that would just give you a nice constant 6, but we'll talk about the examples of taking derivatives beyond acceleration, what they actually mean. Another thing that I want to do is show you how integration play a role in this. And just based on our definition, knowing that acceleration is a change in velocity with respect to time, if I wanted to solve for velocity at any moment, I could rearrange this and solve for dv. That would give me a multiplied by a dt. And if I'd want to know my change in velocity, I'd have to take the integral of a times delta t. So since velocity is a function with respect to time, I've got to integrate both sides. Let's say that our acceleration is constant, just to make it easy. That means I can pull the a out of the integration and just have to take the integral of dt. Integral of dt should be easy. That would give me a times a change in time. Now when we do integration, we need to add in a constant of integration. Over here, dv would give me just v, so this would really be my final velocity, plus a constant of integration. In this case, it would be my starting velocity, which if you look, taking the integral of velocity with respect to time, I end up with that first kinematics equation that we derive from the slope of a line. We can also the integral of our velocity function, because we know that dx over dt gives us our velocity. If I want to solve for position now, dx would be my velocity times my change in time. I'd have to integrate both sides again, and we now know the velocity from last. Putting this in for velocity, I know the dx is just going to give me x, and over here my integration is going to be VO plus AT dt. So that means I have to integrate everything inside this function with respect to time. Remember, VO could be multiplied by a t function, t to the 0 power. If I do each of these integrals separately, I'm going to get VOT plus AT squared over 2. It should look very familiar. The final position of an object is VO times time plus 1/2 AT squared. Again, adding in the constant of integration would be adding in our initial spot. And if I move the initial position to the other side, that'll just give me that delta x that we had last time. Integrating the velocity with respect to time takes you all the way back to give you position. This final section for accelerated motion, we have the examples of freely falling bodies. And if you see in this picture here, it looks just like a motion map, or if you would use your Motion Shot app and drop something out of your window, you would see object be very close in position in the beginning and start to spread out further and further and further as it falls towards the ground. So freely falling bodies without air resistance. So when you do any of the problems here in this unit, anytime we drop them, we assume that there's no friction on it, there's nothing to slow the object down. The only thing acting on this is the constant acceleration of the planet. When all objects near the surface fall, they fall at the same constant acceleration. We'll prove that with some demos in class. So free fall, objects with constant acceleration, and they're only under the influence of gravity. If you drove off a cliff and the officer said you were speeding by the time you reached the ground, you could say, "Officer, I'm so sorry, I was under the influence of gravity." And maybe that'll get you out of your ticket. Since gravity is changing your velocity as time goes on, we call the speed that you gain due to the acceleration of the planet's gravity. We use that lowercase g, an acceleration due to gravity. There are some values and factors for this. We'll again show you that this is true in the lab as well. G can be 9.8 meters per second each second, or if you're wanting to use feet, that'd be 32 feet per second, or if you wanted to use centimeters for whatever reason, you'd use 981 centimeters per second each second. And I'm sure it's in everybody's head now, seeing the headline up there, free falling. So when an object free falls, let's talk about the speeds that you gain every single second. Let's, for this first example, assume that we drop an object from rest. An object from rest has no velocity in the beginning. So it drops with a velocity of 0 because in your hand it was not moving. After the first second of free fall, you can see down at the bottom here, we're going to gain 9.8 meters per second each second. We're gaining that downwards acceleration as a vector. We do have to throw that minus sign in there. For the first second of free fall, objects are traveling 9.8 meters per second after the first second. WebAssign is going to want 9.8 for G. For this example here on the notes, I'm just going to round G to 10. And you can do this on some of the multiple choice on the AP test. Use 10 since it's a nice round number. It means after the second of free fall, we are now at negative 20 meters per second. After the third second, you guessed it, 30 meters per second. After the fifth second, 50 meters per second. At any moment of time, I take my 10 meters per second each second, and all I have to do is multiply by time. So if I fell for 100 seconds under the influence of Earth's gravity, I would be going around 1,000 meters per second. So it's a nice, easy way to remember this. And again, if you're not metrically inclined and you don't understand what 10 meters per second is, and you need that in English units for you, if we started from rest, technically you'd be going 22 miles per hour after the first second, 44 miles per hour after the second, 66 miles per hour, just falling for 3 seconds. And at 4 seconds, you'll reach 88 miles an hour. From here, you travel through time. However, sometimes your problem may not start at rest. If I initially threw the object downwards when the problem began, let's say that I threw an object down at 5 meters per second, my initial speed at the start would be negative 5. So after the first second of free fall, I already have a starting speed of 5. I'm going to gain another 9.8 or 10 meters per second in the next second. So in the first second of free fall, now I'm moving 15 meters per second. In the second, 25. In the third, 35. And by the fifth, 55. So each second I gain 10 more meters per second of velocity for every second that I fall. Really, there isn't much of a change in your kinematics equations. I'll put all three up right here. The first one is still the slope of a velocity graph as you free fall. The second, we change the x for displacement into y's if you're dealing with vertical motion. Same with equation number 3. And the only big difference here is that if you have an acceleration, that acceleration due to gravity ends up being negative 9.8 meters per second each second. I do like writing the acceleration as AG. That way you remember that gravity is an accelerator and you don't think it's just this separate variable off by itself. Now, we can throw things upwards in the air, not the throw up that you were thinking. In freely falling upwards example, what I mean by that is recall that when you throw the object into the air, it will have an upward positive velocity. On the way down, it will have a negative velocity. And at the top, that's the turning point that we've stressed so much. So we've got this example here, launching a ball in the air with an initial speed of 29.4 meters per second. Draw a sketch of what's happening. How long does it take to reach the top? How long does it take to come back? And what is the velocity when it returns to you in your hand? That 29.4, I'm going to round to 30. So that means that my initial velocity is plus 30 meters per second. My acceleration is going to be negative 10 meters per second each second. Remember, for WebAssign, please use 9.8 or you'll be getting red X's. So our scenario is going to look like this. Scenario is going to have the ball launched upwards with an initial velocity. Then that object's going to slow down, stop at the top for a very brief moment in time, not even a second, snap of a finger. It's going to be heading back down, and going to be heading back down. The first question was asking, how long does it take to reach the top? Well, knowing the initial information, 30 and negative 10, I know that my final speed at the top must be 0. And if that's the case, that gives me 3 pieces of information. We said you always need 3 pieces of information to solve any of those kinematics equations. Quickly, using that first equation, plugging in your values, you know that initial speed is 30, final speed is 0, acceleration is negative 10, and we're looking for the time to the top. So if you take 30 divided by 10, it's going to be 3 seconds to reach the top. Or if you remember the definition of acceleration, if I'm starting at 30 meters per second and the acceleration due to gravity is a downward negative acceleration the entire time, I know that for every second of free fall, or as the object's moving upwards, I'm going to lose 10 meters per second for every second that I'm in free fall. So if I'm starting at 30 with these 3 lines, the next second I must be going 20, the next second I must be going 10, and at the top I must lose the rest of my velocity and be at 0. So here's time 0 at the bottom, 1 second, 2 seconds, 3 seconds to the top. The old saying goes, what goes up must come down. That means after 1 second of time, I'll be going negative 10 on the way down, negative 20 on the way down, and then negative 30 before I reach the ground. That means it's going to take 3 more seconds to reach the ground. So total time in the air, total time, ends up being 6 seconds. Time to the top, 3 seconds, 6 seconds back at you, and the velocity when it reaches the ground is right here. It's 30 meters per second. The only difference is it's negative because it's coming right back at you. So what goes up must come down. The time to go up equals the time to come down, and whatever you throw that object into the air must come back at the same velocity. In a perfect scenario, without air resistance, never ever fire a gun straight up in the air. What goes up must come back down.